All right, welcome back everyone to ECE 590i seminar. Today we have John Reband with us. John Reband is an aerospace engineer employed at the U.S. Air Force Research Laboratory, Aerospace Systems Directorate in Dayton, Ohio. His work experience includes design of revolutionary aircraft configurations, experimental research on advanced aerodynamic technologies, and management of government research contracts. John received his bachelor's degree in aeronautical and astronautical engineering from Purdue University in West Lafayette, Indiana in 2017, and has been studying electric machine design and power engineering at UIUC since spring 2020. His research interests include aircraft conceptual design methods, electric vehicle powertrains, and spacecraft architecture. Thanks for being with us, John.
All right, thanks for that introduction, Max. I'll go ahead and get started. So good afternoon, everyone. Again, my name is John Reband. I'm going to be presenting a summary of my thesis work on sizing electric powertrain hardware for conceptual design of aircraft. So before I get into the details of my contribution, I want to give a little context on my graduate work. My background is in conceptual aircraft design. I've been working in that field since I started working at AFRL right after graduating from Purdue in 2017. And while there's a few groups at AFRL who are doing really good work on electric aircraft, there's a critical lack of personnel with cross-disciplinary knowledge that I think is needed to drive effective collaboration between the technical experts in the different fields, primarily aerospace and electrical. And I think this is reflected in a lot of different organizations who are working on this problem. We just really don't speak each other's languages. So my goal was to come here to get enough exposure to electrical engineering to help facilitate that level of collaboration. And so I think my work as a result of that might display a little less technical depth in both fields than my peers who are working on one or the other in those silos. But I want to emphasize that what I did here was try and build technical breadth, which is necessary to advance electric aircraft design. I believe I accomplished that goal, and my thesis is reflective of what I learned here. So with that out of the way, I'd like to take a minute to discuss the motivation for studying electric aircraft. Many of you are also involved with this type of research, so I'll be brief. But I do think it's important to be clear on why this research is worthwhile. Contemporary aircraft powered by hydrocarbon fuels already work pretty well, so why do we care? And electric aircraft aren't a new idea. The first fully electric aircraft flew in 1973. It was a motor glider that was adapted to fly entirely powered by nickel-cadmium batteries. And since then, there's been a number of successful manned and unmanned electric aircraft that have been built and flown. But the poor energy density of electrical energy storage compared to chemical has really relegated most electrical aircraft to the experimental domain. But improvements in the relevant technology fields might be changing that. And I think the expected benefits of electric aircraft are captured really well by just a few major points. First, electric aircraft don't produce tailpipe emissions. And while the actual lifetime emissions of the vehicle are dependent on how the energy is renewably generated, which might be from non-renewables that support the grid, it's been determined that emissions at a high altitude actually have a greater proportional impact on climate change than the same quantity of emissions at sea level. So driving down tailpipe emissions it's a non-zero sum game. It's actually worth, even if it's the same level of emissions being produced, it's worth to do that at ground level rather than in the sky. Secondly, we expect that electric motors may have reliability advantages over jets. Turbines are very mechanically complex and they require constant maintenance, whereas the simplest electric motors can have just one moving part. Additionally, it's more feasible to operate many small electric motors than many small turbines, which can reduce the consequences of a single propulsor failure. And this relates to another beneficial point, which is the suitability of electric motors to airframe propulsion integration. And in essence, what this term means is the synergistic design of the propulsor and the vehicle outer mold line to work together aerodynamically, as opposed to traditional aircraft, which basically decouple the performance of the propulsion lifting surfaces. We typically treat these subsystems separately in conceptual design, which simplifies the design process, but research suggests this decoupling may lead to suboptimal performance. And finally, there's cost. And not only is electricity generally cheap compared to jet fuel, but running an entire fleet independently from fuel prices makes it a lot easier to run a business and keep ticket and shipping prices consistent for commercial operators. So the volatility of fuel prices is a huge driver of the volatility of the aircraft industry. And the cost advantages go beyond just the cost of building and operating one vehicle. The real cost comparison with electrical aircraft with conventional aircraft really only makes sense when you look at the fleet level economics and you consider a representative cost of reducing the environmental impact, right? You can't just look at what are the costs to build and fly. You got to see what are the costs of the entire economy of switching to these type of vehicles. So with that background, conceptual design is the first stage of the aircraft design process. And during this stage, designers are trying to lay out the overall configuration of the vehicle and come up with reasonable initial estimates for the mass and performance qualities. Essentially, the goal here is to achieve reasonable certainty that your aircraft can meet the design requirements, but do so quickly enough you can explore the design space in meaningful breadth. Because design and performance of the subsystems are all interconnected, it's a very iterative and non-deterministic process. However, it's really well canonized in existing literature and has been proven in practice. And what I mean by that is we can design conventional aircraft very quickly using existing methods and be confident they'll meet our performance expectations. Again, at least for conventional aircraft where we're assuming that they are turbines that burn fuel. The main pivot points of the design process have arguably been constant for the last century, which is basically the entire history of human aviation, as can be seen through Frank Barnwell's articles, which summarize design techniques and originally published in 1916. So you can draw clear parallels between the design processes we use today and the points that he laid out all the way back then. So to briefly run through the canonical strategy, it begins with requirements generation, where we look at the mission the customer wants to do and translate that into performance metrics for the aircraft. And these are things like airspeed, endurance, payload capacity, etc. And next comes the weight estimation, where we take a stab at the initial mass of the vehicle based on payload performance requirements. And it's usually an empirical method that we use there. We then generate constraint curves, which bound the design space based on requirements and determine how much thrust and wing area is needed. I'll speak a little bit more about the constraint curves later, but essentially all you need to know is they're derived from a single master equation, which relates the forces on the aircraft to its design specifications and the desired flight performance characteristics. And that master equation can be broken down into a number of different constraint curves for things like cruise speed and stall speed and climb rate and things like that. From there, we select this point on that constraint diagram, and we conduct configuration design, which describes the shape and placements of the components like the fuselage, the lifting surfaces, control surfaces. And once we have the rough shape and layout of all the components, we can go ahead and do a detailed mass estimation and refine it component by component. So we go piece by piece and we get a more accurate guess at the mass, and we compare that with an initial mass estimate that we did before the constraint diagram. And this is usually the point where there is the most iteration, right? If it's way off, if our detailed mass estimate is way off from our initial mass estimate, we go back and do it again. And with all this information, we can analyze the performance of the aircraft in detail, and there's usually some experiments or at least detailed CFD to further understand the capabilities of the vehicle that we've created to be confident that it'll do what we need it to do before we move on to preliminary design and more detailed phases. And one of the most important characteristics of traditional aircraft design is that there's a huge reliance on empirical and semi-empirical methods, meaning that it's all based on interpolation from data on existing aircraft. As an example here, this graphic on the right is from Raymer's design book, and it's used for predicting an aircraft's empty weight as a function of the initial mass estimate for different classes of aircraft here. So you can see we have like jet transport, that'd be a cargo plane or an airliner, agricultural aircraft, fighter jet, that kind of thing. There's different, and you see this kind of thing a lot where there's different models for different classes of aircraft. And this type of model is really the backbone of traditional conceptual design. The reason that we use empirical models is because it allows us to get close to the answer without needing to know every single number that defines the aircraft. So it's kind of a trade of accuracy versus fidelity and computational load of the model. And the name of the game is really getting a pretty good estimate without knowing all the little details like the number of rivets in the wing. Because if you took the time to generate all those details, you wouldn't be able to compare many designs at a high level, and you would risk ending up with a suboptimal design because you didn't adequately explore the design space. It's sort of a version of the exploration versus exploitation trade that we talk about when we discuss optimization techniques. The problem with these methods is that because they're empirical, they're really not well suited to aircraft whose design or technology departs significantly from the vehicles that were used to derive them. So in the case where we have electric aircraft, we have an entirely new method of storing energy and transmitting energy from onboard the aircraft into propulsion. The likely parameters that define a well-designed electric aircraft are probably not reflected in those models that were derived from conventional aircraft. That being said, as computational power increases and we learn how to do physics simulations more efficiency, the popularity of physics-based models is increasing in aircraft design, which is good if we want to design aircraft with new technologies that we don't have empirical models for. So we see there's a need for effective design processes for electric aircraft, even though the prevailing opinion within the existing literature is that technology needs significant advancement before electric aircraft will be remotely competitive with conventional ones. Having good design methods helps us assess the viability of electric aircraft given the current state of technology. which is exactly what I've tried to do here. So for example, if someone demonstrates a new inverter that has 200% better power density than the existing designs, we want to take that number and see what it means for the performance of the vehicle. So we can say, okay, how competitive are electric aircraft now with normal aircraft, given this new technology? So how did I go about adapting the process from conventional design? So I started by generating an n-squared diagram, which is shown here. And what this does is it maps the data that form the interfaces between the various tasks in the design process. And I then consider all the new processes that we would need to account for electric powertrain design and put those into the n-squared diagram. So these are these pieces in orange here, outlined in orange, that were added to the n-squared diagram. And the framework essentially serves as a map to guide my selection of the different component models. It tells me what information these models are receiving from previous steps in the process and what information is providing to the next steps of the process. And you'll notice there's a great deal of interdependency and feedback in this process, which translates to a need for either really careful iteration or robust optimization to reach the optimal design. So with the overall design framework established, we can move on to novel component models. So there's three major components of electric powertrains that really aren't well captured by the existing methods. The first is propulsion, which is provided by electric machines instead of turbines. And a useful way to analyze electric motors at low fidelity is the shear stress method, which generates torque capability by considering the shear stress at the rotor surface. So all you really need to know to figure out what torque the motor is capable of is the volume of active material and the peak electrical and magnetic loading. And then those second two parameters you can estimate from existing designs in the same power class. So in this case, I'm using a conventional motor in the megawatt class. So I took these numbers from the 1 megawatt machine that Professor Heron's group built for NASA. It's worth noting that the strategy of keeping a constant electrical magnetic loading and then scaling the active mass has worked out well for us during other research efforts. Meaning the designs that come out of this method hold up in detail analysis, and I'm confident that it's of appropriate fidelity to be used here. And for this study, again, I've only considered conventional radial flux machines, so no superconducting, no axial flux. The next piece is the energy storage, and the real challenge here is that sizing electrical energy storage is fundamentally different from sizing fuel tanks for a conventional aircraft. So with fuel burning propulsion, you can size the engine for power and just add jet fuel until you have the energy you need to complete the mission. But for electrical energy storage, those devices have to store both the energy and the power. It has to be able to discharge that energy fast enough. So the best system is probably a split between devices that have lots of energy per unit mass, like batteries and fuel cells, and devices that have lots of power per unit mass, like supercapacitors and ultracapacitors. So the ratio of how much each type of storage makes up the total mass, which is this H variable here, I have H high energy density and H high power density, becomes a new design variable that we have to select during the process. And lastly, we can expect inverters are going to make up the bulk of the power electronics, since all practical energy storage devices produce direct current and AC machines have demonstrated the highest power density. So I assume the best in contemporary energy and power density for inverters, and I tack on another 5% of the total powertrain mass for transmission and distribution hardware. And that was just based on amalgamation of results from several more detailed design studies that have been published. So with this new design method laid out, I conducted a design study on a medium altitude, long endurance sensor craft to see what kind of results I would get. And the reason I chose this mission is because this mission would be served pretty well by an electric powertrain. For one, it would be quiet, which is good. And second of all, if you can get fast charging technology, you might be able to do faster sorties, right? So there's an interesting trade there between how long you stay in the air and how many missions you can do in an amount of time. So I started by generating expression to estimate the initial mass, right? This is one of those pieces that we don't have for electric aircraft that we do for conventional ones. And after several iterations, I arrived at this equation here at the top right, which scales the mass of the new vehicle I'm designing from a reference vehicle mass by the ratio of endurance and energy density of the new vehicle to the old vehicle. So I start with the endurance that I want and the energy density of my electric systems, and I scale it against the energy density of jet fuel and the endurance of my reference vehicle. In this case, I use the MQ-9 Reaper as my reference vehicle because it's designed for a similar mission as I've considered here, so long endurance, medium altitude. And this led me to an initial mass estimate of 50,000 kilograms for the vehicle. After doing a buildup of all the non-propulsive elements, I was left with a budget of 38,000 kilograms to fit my entire propulsion system. So that's, including the wings, including the fuselage, structural elements, avionics. 38,000 kilograms is what was left for all the propulsion electrical pieces. With this information, I generated the constraint curves I talked about before on the thrust versus wing loading diagram. So that's on the left here. So from that master equation, based on my desired cruise speed, desired takeoff equation, desired takeoff distance, desired climb rate, and desired stall speed, I formed this this area here above all these curves, which represents the valid design area. And I selected a point in this region with high wing loading in order to keep the wing size down, because this ends up being a pretty heavy aircraft. And I want to be on the conservative side for the wing structure. I don't want it to be too small or too thin. So I selected that design point, and I want to know that all my assumptions and models here are based on the best contemporary technology, at least at TRL 7, meaning the devices have been demonstrated in a relevant operational environment. So there's a lot of exciting developments, particularly in battery, capacitor, inverter technology that are much better than what we have today that might come in soon. But I didn't want to take any credits for what might be online in the next few years, right? I wanted to use the best working technology today to see what that means for the performance of the aircraft. So with this mass budget, the next thing I did was a trade study to find the best split point between the high energy density and the high power density storage devices. So essentially for each split point going from 0 to 1, this is all, 1 is all batteries, 0 is all capacitors. I did an estimate based for energy and power, right? Based on the average energy and power based on the split between these two devices. And then took the greater of those two to figure out what the actual mass should be. So whether or not it needs to be sized for energy or sized for power. You can notice the minimum weight comes here around 97% batteries, which makes sense because we really only need maximum power for a few minutes of takeoff. After takeoff, the power requirements of the vehicle drop off drastically. And so we want to use the minimum amount of those low energy density capacitors. And you can see here where this kink is, right, where it starts going up again. This is the point where you don't have enough capacitors, so you have to start adding batteries for energy purposes. And the volume also skyrockets because you have so many batteries. After completing the sizing for each powertrain component, I built up the total powertrain mass estimate here, and I came up with 40,000 kilograms, which is actually only less than 5% from my budget, which is really encouraging for conceptual design. For some context, usually with conceptual design, what you come up with in conceptual design compared to the final vehicle, there's about a 20% difference there. It's within 20% depending on what parameter you're looking at. So this is a really good endorsement that the technique I presented here is of appropriate fidelity. Briefly, I want to address modeling of the powertrain components. Again, it needs to be reasonably representative of the performance for the size components, but low fidelity so you can run it quickly and easily in order to be appropriate for conceptual design. We have simple low fidelity tools for aerodynamics, structural, turbine engine performance that we can easily fold into an optimizer or even do by hand, but it's not clear what fits into that space for electrical components. One common theme I picked up from speaking with experts is we don't have these kinds of models because you need some kind of representation of control scheme in a power simulation to know with any confidence whether or not the system is capable of performing the drive cycle needed to fly the mission. So for my purposes, I use PSIM to validate my powertrains, but it required a lot of assumptions. So I use field-oriented control, and my choices of the motor design details like slot number and tooth width and such were influenced by results from other aircraft motor design studies that we've done here for other research projects. So working knowledge of motor design can help mitigate this problem, but I really do see a need for a purpose-built aircraft powertrain tool that hits the appropriate point on that accuracy versus fidelity curve. So to briefly conclude, what I've done here is I presented a suggested method to size an electric aircraft powertrain and demonstrated promising results that suggest the method may be of appropriate fidelity and accuracy for conceptual aircraft design. And the usefulness of this method comes in the translation of the capabilities of components to the vehicle level performance metrics, which allows us to continually assess the viability of electric aircraft over time as technology improves. So as an example here, the new design I've come up with is about the 50,000 kilogram weight class, flies at 200 knots and has an hour of endurance. Compare that to the Embraer E190, which is a very small passenger jet, about the same weight class, but flies much faster and has a much larger endurance. So here we've demonstrated what is the performance gap that's caused by the inferiority of electrical energy storage to jet fuel. And we can continue to do these kinds of studies as technology improves with new numbers to see how that closes the performance gap. One thing to note here is that I've looked at one technology, right? I've looked at electrical propulsion technology, and this is probably not the only time that we're going to have to adjust the aircraft design process for a new technology, right? We already have the jet engine revolution, and now we have the electric aircraft revolution. So we need to think about how do we implement arbitrary technology X into aircraft design. And really what it comes down to is understanding the interface of that technology with the rest of the vehicle, right? So as I described earlier, I took my n-squared diagram, I built in the electrical tasks to size the powertrain. but you also need to understand how the implementation of the technology affects the design of other components. So for example, I had to size my landing gear to be much bigger and heavier than you would for a normal aircraft, because conventional aircraft, the landing gear is usually not rated for landing at full takeoff weight. So if an aircraft takes off and has to land right away, it usually has to dump some fuel. In this case, electric aircraft don't burn fuel. They're the same weight the entire time. So I had to make sure that my landing gear was beefed up enough to handle that additional weight. So it's things like that you have to understand and consider how the implementation of this new technology affects how you need to design old technologies aboard the vehicle. What I've shown here is just one design study with one vehicle. It's probably pretty far from optimal. I only went through the iteration a couple times to refine it. We won't really know if this method is useful or valid until we have lots of successful experiments, at least detailed CFD, right? Truly, we need flights. We need to build several vehicles of different sizes and different capabilities and test them to see if the method works out. But I think this is a good step in coming up with that robust methodology. In terms of future work, again, empirical verification, we need flights to ensure that. We need to actually build the vehicle and see if it flies to know if the method is any good. Hybrid powertrains, most effort has been focused on hybrid powertrains, again, because of the inferiority of electrical storage capability. In the literature, most people deal with hybrid powertrains the same way that I dealt with capacitors and batteries. So they have like a split variable that defines how much power comes from each system, and they adjust that and see what kind of difference that makes in the design study. Exotic motor topologies. So again, I only consider conventional radial flux motors, but there has been some promising research for aircraft applications, specifically on axial flux machines, DC machines, and then of course superconducting machines. With the superconducting machines, you'd have to have some kind of loop in this process to account for the cooling hardware, because that's going to be pretty significant in order to keep the conductor temperatures where you want them. Tool development, as I mentioned, I think there's a space to, there's a need to add an electrical tool in the space, right, of appropriate fidelity for conceptual design. And I'd like to continue contributing to work on that. And then cost estimation. Usually conceptual design has some kind of cost estimation. I don't have that here, but it's really helpful to know, okay, if I take a small hit in performance, I have a different design that's much cheaper. And that's good for the customer to know when you're actually choosing which design you want to go with. So that's the end of my prepared material. I want to thank Professor Herron for sponsoring and advising me during this project, and of course, my colleagues at the U.S. Air Force Research Laboratory. If anyone thank you for your time. Thank you for listening in. If anyone has any questions or comments, I'd be happy to take those now.
Thanks so much, John. Do we want to do a last call for any questions? Hearing none, I don't think there are any. So thanks a lot, John. That was really interesting. Like, learned a lot about what our own group does. So
All right, well, yeah, I have my contact information up there. So if anyone has any other questions, wants to follow up, please do. Otherwise, I think we're good for today.
Yep. Thanks.
Thank you, John.